Good evening. Thank you so much for coming. It's wonderful to be back at Gresham College. It's a few years since I retired as Gresham Professor. I think I've been back every year since then, which has been wonderful. I'd like to thank Gresham College for allowing us to have this book launch here and for me to give a talk on astrophotography. You probably know that I've been at Jodrell Bank since 1965. That's, I think, my 52nd year. I still go out 2 days a week. I'm doing a project there. They just forget to pay me anymore. But since I was, I think, 11 or 12, I was given some lenses by my optician. I had to wear these very thick glasses from then. And I made a little telescope out of cardboard tubes and probably toilet rolls and things. And I could certainly see the crater on the moon, the moons of Jupiter, and perhaps one or two other things. And a lot of people tend to embroider their past a bit. And Sir Patrick Moore was a bit inclined to do that. But anyway, I know that I did have a real interest because I won the odd physics prize and actually the music prize at school over the years, and they were all astronomy books, like Every Man's Astronomy. So I must have still been interested. And I was able to do a little bit of astronomy at Oxford University before becoming a radio astronomer. But in fact, I've been interested in amateur optical astronomy all my life, really, and I had a 10-inch telescope when I was about 27, which was quite a sized telescope, 50 years ago or so, whatever it was. And I helped found the Macclesfield Society way back about 26 years ago. I'm now, as you can see, its patron, and I was president of the Society for Popular Astronomy way back around 2000. I still am on its council and help people with their choice and use of telescopes. So I have been very much involved in amateur astronomy. And a few years ago, perhaps about 6 now, I started trying to teach myself a bit about astrophotography. And that's what this book is all about. So let's begin. The idea of the book, which they've got some copies out there, just in case, is there are about 20 odd chapters, 22 I think. 4 of them relate to general things about astrophotography, some of them mentioned, but the others are all basically case studies, starting initially with a camera and a tripod. It tells you what you need to do something, how to take the pictures, which is quite important, but most importantly of all, how to then process those pictures to produce a nice image. That's where a bit of the art comes. So let's begin. So an introduction, a camera plus lens on a tripod, that's all you need. And one of the first things, and perhaps the easiest thing to do, is to take a star trails image. And they can look very lovely if you go on the web. Now, the place I went to is called Reedsmere. It's not far from my home in Cheshire, south of Manchester, I might say. And I promise you, it does have a view, can you see the north there, directly towards, oh, it's gone. Oh, next one, sorry, here. I'm seeing 2 screens here, it's quite complicated. Anyway, so it's looking north and it's got a nice low horizon. I have taken astronomy groups there quite often because it's pretty dark. It's one of the darker places in North Cheshire. There's only a slight problem. There's quite a good car park here, and I said it's dark, so at night when we've been there doing astronomy, you sometimes have quite a few cars where the occupants probably are not interested in either ornithology or astronomy. And I must admit, I was a bit worried about going here to do what I'm going to show you, in case that was what was happening. In fact, luckily, it was 0 degrees Celsius as I left home, and it was -4 when I left Reedsmere, so I thought I'd be okay. There was still one car at the far end of the car park. How they kept warm, I don't know. Anyway, so what I did, I pointed my telescope directly at the pole star. Sorry, my camera, forgive me. And can anyone see a little dot here? And that's the plough. You see, this is the light from Manchester, and up here is Cassiopeia. And I took 100 pictures before my lens, 30-second exposure before the lens dewed up. The way to get around that is very, very simple, very cheap. You just take a nice thick sock, you cut the end off, you push it over the lens and stuff a couple of hand warmers. You know the little things you get? Only cost you a couple of quid, and that would do it. But anyway, I was there for 50 minutes. I took 100 exposures, and that was the first one. So the way to do it is so easy. There's a wonderful program called StarStax. And all you do is you put in all the pictures, you download them, it says here, drop images here, and cleverly, up here, it has a thing called gap filling. Because can you see there's always a little gap between you pressing and taking one picture and the next one? And I was doing it manually, so there's a few seconds, and it just fills the gaps. So that's great, and that was putting them all in. That's not all of them, about half of them. And this is what you get when it's worked through, just over half, and that's what it got when it had done the whole lot. So you see the trails there. Now, that's not very artistic, so what I did then was just to go forward a bit because there's some rails in front of me, put the camera down and take a photograph of the lake and just merge the two together. And that was the result, which actually is the front cover of the book as it happens, because the CUP rather liked it. Anyway, so that's how to do it. I always think it's good to point your camera directly at the pole star, because then any distortions in the lens don't make things go oval or funny shaped. So that's how to do it. So it's very simple. All you need is a program called Star Stacks. Okay, so what else can we do? Well, again, with a camera just on a tripod, looking up at the plough. You all know where the plough is. And I took 20 exposures, 10 seconds long. You can't take too long exposures just on a tripod, because as the Earth rotates, the image, the stars will trail. There's a way around that we'll come to. I then put them in something called Deep Sky Stacker, more of which a bit later on. And what that does very nicely, it looks at each image and it aligns them all. It even derotates them, which is something you get just on a tripod, and adds them all together. And I got a total of 200 seconds from it, which was not too bad. Now, what comes out of Deep Sky Stacker doesn't really look any better than what you get with a single image. You need to what's called stretch the image, because the Deep Sky Stacker has a lot of bit depth and a lot of the information is way down below what you can see on a simple screen. So you can go into another free program called Iris, and that will actually stretch the images. So here, can you see the plough? That's here, and over there, Alcor and Mizar, you can see. Now, digital cameras are better than, in some respects, than film. In film cameras, the brighter stars tended to look larger because of what's called halation. They stand out more. There are ways round that if you have an image like that, and whether you want to do it or not, there are techniques to enhance the brighter stars, and that just shows the brighter stars a little bit more obviously. So you can play around to your heart's content. Both of those are done simply using a camera on a tripod. Well, you can do a bit better. There are things called tracking mounts, and there are 3 of them, and they basically rotate the camera around at sidereal rate to compensate for the Earth's rotation. And there are 3 there. These are about the size of cameras, really. This one is a little bit larger, and you can do some lovely things with them. This is not my picture, it's one of a couple that aren't mine here. Can you see Orion, the hunter? Here. Those are the Pleiades, here are the Hyades. That's actually Jupiter. And that was a 10-minute exposure. Now, without a tracker, you couldn't do more than about 20-30 seconds. So it's a great help. Can anybody see a hint of red around there? A little bit? Well, you'll see that a bit later on writ large. Well, I've got several of these actually. This is my AstroTrack. Now, the precision of the tracking is basically depends on how big the gear is. And these little ones have gears about that size, but the AstroTrack, the way it works, the effective gear is that size, because it's done at the end of a long arm. And the net result is it tracks exceedingly well. It's a little bit bulky. So when I go abroad, I go to New Zealand quite often because my son lives there. I don't really want to take something as big as that. I like to have my kit in my carry-on luggage, and I think they have something like a 7-kilo weight limit now. They don't seem to bother to weigh it very much. So I was using, I think, the smallest setup that you could possibly have, and it's on this little picture here. A device called a nano tracker, which sort of implies it's quite small, isn't it? It's about the smallest tracker you can have. That's its little power pack here. I was using a thing called a micro four thirds camera. Does it mean anything to anybody? They're smaller than DSLRs, slightly smaller sensor, still quite good, but with it, an absolutely superb 20mm lens. I've got some Zeiss lenses, I've got some Leica lenses. I used to collect cameras quite a bit. This is probably the best lens I've got if you stop it down a bit, it's sharp from corner to corner. And I've used that in South Island, New Zealand, to image, this is the centre of the Milky Way, and it's upside down, I'm afraid. That's Sagittarius, you know the teapot? That actually is called Corona Australis, and this is the bottom bit of Scorpius here, and some very nice open clusters. I was there just a few weeks ago, and this particular part of the sky was visible. It's a lovely part, actually. Alpha and Beta Centauri, the Crux, the Southern Cross, Carina with a lovely nebula here, and then the False Cross. And up here, Omega Centauri. And that's the picture that I took straight out of the camera pretty well. But the bright stars don't show up very well. I had another go when it was very hazy and the stars looked bigger. I enhanced them a bit and sort of combined the two. Alpha Centauri, the nearest star system to the Earth. Beta Centauri, not as bright, but it's 10 times further away. And it's very, very bright. It's one of the brightest stars we can see with our unaided eye. Then up here is Omega Centauri. It used to be thought to be a globular cluster, but now we believe it's the core of a galaxy whose outer stars are stripped off. It may even have a black hole at its heart. Here I think you can see the Southern Cross. Down here is a nebula region called the Carina Nebula. This in fact is the Southern Pleiades, and that's the False Cross down here. Now that nebula there contains the star Eta Carina, which is the next star that is probably going to be seen to blow up, a hypernova. It's a massive star system, maybe 100 solar masses. And when that goes bang, we'll know about it. It's quite good, that. So that's what you can do on a tracking mount. Now, I went to Kerry last summer, and the very southwest of Ireland is also one of the world's best 3 dark sky sites. You know, there's nothing there, is there really? Nothing as you look out to sea. And this was the first picture I took, and other people came up to me and said, "Are your pictures green? Does that look a bit green?" I think it does. And we looked at it and said, "Wow, what's that?" We thought about it, and we came to the conclusion that it's what's called air glow. This is a picture from the space shuttle. Now, have anyone seen the aurora, the lovely green colour? That's oxygen giving off a particular spectral line, the O3 line, with the atoms excited by the impacts of particles from the sun, the solar wind. But here, the atoms, so I'm not doing very well, the atoms are excited by ultraviolet light from the sun during the day, and they cascade back down, giving off that lovely green glow. Well, you can get rid of it, and that was an attempt I made at the Milky Way as seen from Kerry. Okay, well, let's move on a little bit. We can use small refractors. And the ones we use for astronomy tend to have at least one element of what's called ED glass, extra dispersive glass. Most camera lenses you buy now, have you seen the word ED on them, anybody? It basically helps reduce chromatic aberration. And this is one there that I've had for quite a while. I'll show it to you. There we go. Very nice one, in fact. Very nice and compact. And one thing you can do with these, actually, is to use them for nature photography. Because there's only 2 elements of glass, as opposed to perhaps 10 or 12 in one of these big zoom lenses you pay 6,000 quid for, this is about 400, I think you can get better images. And I have been to that same place, Reedsmere, in the daytime, and that was one picture I took of a mute swan, which actually was on the front cover of a magazine. I couldn't understand why they wanted it, because it was nothing to do with swans, but the magazine had moved its offices to Swan-Upping, wherever Swan-Upping is, so that's why they wanted it. Now, there are several ways, 2 basic ways of using a telescope with a camera. The simplest is to use a compact camera with a little zoom lens on it. This was a Canon G7, I think. You set up the telescope with an eyepiece, just as you'd use it visually, and you can buy a little stage like this that mounts the camera so the lens of the camera is on the optical axis of the eyepiece. You get the idea, so it's all lined up. You can actually hold it by hand, but it's easier with one of those, and you can take a picture of the moon, like that one on the right. Now, typically, images of the moon tend to look a bit flat. The contrast isn't very high. There are techniques to make it somewhat better, as you can see in that central picture here. Again, it isn't actually black and white, it isn't monochrome, it's actually slightly coloured, but often they look better, as on the right-hand side, when you take the colour away. The other thing you can do is to use a proper DSLR, or actually one of these Micro Four Thirds cameras. What you have is a barrel that goes into the focuser of your telescope, and then a specific little adapter that screws on there that has the right bayonet, to go into your own camera. So the two of them are called a T-mount. That's fine. The trouble is you nearly always need to have the camera further away from the telescope objective than the focuser will let you do. So you often need to have a little barrel extender. It just makes the focuser a bit longer. Again, if you're looking at the moon, the images, if it's a small telescope, aren't very big, and there are things called Barlow lenses that basically 2 times they double the size of the image. So I've had a go with those. That's just one image I took using a 70mm, quite a small telescope. This is Mare Crisium, Mare, oh dear, I forget these, that's Tranquillitatis up here. That's Copernicus and Plato, Sinus Iridum, often said to be Sinus Iridium. It's Iridum, the Bay of Rainbows. Now this one, I've slightly accentuated the colour. Can you see that's somewhat bluer than that? This is Tranquillitatis, I think that's Serenitatis, and the reason is that that particular crater has more titanium in the lava than the others. So you're doing a little bit of lunar geology, not a lot, just a little, but then that's quite nice, they look quite pretty. Another lovely thing you can do is to try and image the moon when it's very, very thin crescent. It's normally you do it in the evening when it's a waxing crescent. And on this occasion, from the Isle of Wight, where it's pretty dark, I took one picture exposed for the bright part, the bit that was lit, a much longer exposure for this, and I was using a really lovely telescope, so the light from this didn't really scatter too much, and then I sort of put those together to make a composite. So that's sort of earth shine. That's done quite well in competitions. Another thing you can do, every so often we get a lunar eclipse, do we not? Sometimes people say, why do they look red? How many people know why they look red? No obvious hands. Look, if you were on the moon and you looked at the Earth at a time of lunar eclipse, the Earth's disk would look black, wouldn't it? But around it you'd see a red rim, which is the sunlight that's being refracted around the Earth's atmosphere. So that's what illuminates the surface of the moon, why it looks that colour. If you've had a major eruption, do you remember Mount St Helens? Quite a few years ago. Well, for a couple of years after that, you hardly saw the moon during the eclipse. There was so much dirt in the atmosphere, it just cut all the light out. Here's another example, imaging the Pleiades. You know the Pleiades cluster, I mentioned it slightly earlier, done with a 72mm telescope. For these things, you don't need big telescopes, because the bigger the telescope, the smaller the field of view. And that is what you get with a single exposure. So you can see the main star of the Pleiades, but not much else. What you can do is to add many of these images together, and that helps you reduce the noise. And here's an example. This actually is M51, a little galaxy. That's 48 seconds, 96, 192, and 384. Would you agree the amount of noise goes down quite considerably? So what we do is we take lots of short exposures, and then we put them into a program I mentioned called Deep Sky Stacker. That takes them all, and you just put them all in, and it will then align them all and rotate them if necessary, add them together to give you the result. And disappointingly, the result that comes out of Deep Sky Stacker doesn't look any better than a single exposure. It doesn't, does it? All the fainter stars are there, but they're hidden down in the bit depth. The screen can't show them. So what we then do, there's several things you can do, but the cheapest, simplest, is to use a program called Iris I mentioned. You put them into Iris, and then what you can do, it has a thing called logarithmic view, and it stretches it to make some of the nebulosity in the Pleiades show up, and you can play a little bit with that, and that was the result some years ago, probably of about 1 hour's less than that total exposure. I had another go at the Pleiades just a few months ago, and that was the image. It's a little bit sharper, isn't it? A little bit better, slightly bigger telescope. But the fun thing was that on it we noticed a little streak. Now I hope I can point it out to you. It's there. Does anyone see a little line there? I'm going to zoom in. It's there, isn't it? It's real. And that was an asteroid that was in fact passing in front of the Pleiades. And knowing the time when it first exposed and the time when it last exposed, we knew the time very accurately. You could work out which particular asteroid it was, and also, in fact, how far away it is. It's about 3 astronomical units from the Sun. It's called 769 Tajana. That was quite fun. That was quite interesting. We didn't know that was going to be there at all. It's a bit of luck. That's it. And I could measure the number of pixels across, so I knew precisely how far it had moved. Each pixel is 3 arc seconds. And I think that total length was 27 arc seconds. And from that we could work out quite a bit. That's a bit of astronomy, you know, just taken from a pretty picture. Okay, now, have you all heard of the Orion Nebula? It's a lovely region. It glows a rather deep red colour here. This isn't my picture. It's a lovely one though, and it is a really difficult thing to image. Partly because a lot of the light is in the deep red. It's called H-alpha emission, and we have a problem that normal cameras, cut off virtually all but 25% of the light at that wavelength. It's so the image from a DSLR matches what our eye sees. Our eyes are not very sensitive as you go down the spectrum. So what one can do is to modify a camera. This is the filter transmission from a Canon, and that's the H-alpha line. Can you see? There's not much of it going to be, 25% probably. So what we do, and there are firms that do it for you, is they take out the filter that does that, they replace it with a filter made by Bada, and can you see it's totally flat here, and then it drops like a stone. You've got to cut off the infrared, and that means you can see a lot more of that lovely colour. So I imaged the Orion Nebula with a relatively cheap Canon camera, which has been modified. I got it. There's a wonderful website I don't dare look at anymore called UK Astro Buy Sell, and it's on eBay for astronomers. And I bought nearly everything I've got from there, actually, and it's too tempting sometimes. But anyway, I got that camera modified for about £220, which isn't too bad. Okay, so what do you do? Well, it's a very difficult thing to image well, because there's an incredible brightness difference between the central part, which is around the trapezium here, and the outer parts of the nebula. You can't see them at all. So in order not to overexpose the centre, I had to have only 12 seconds exposure. All right? But that doesn't show anything of the rest of it. So what I did was to take a large number of those, and oh, by the way, that's just to show you. Can you see the trapezium here? That's not overexposed. Many images you see on the web, it is overexposed. I added them all together in Deep Sky Stacker, and again, what comes out of Deep Sky Stacker looks terrible, but you put it into Iris. Can you begin to see some of the structure? Now, there's no real colour there, but the program called GIMP, which is free, I use that to highlight, to enhance it somewhat, and then I produced the image. But the trouble is that the outer parts of the nebula, so faint, they were very noisy. The central parts of the image were fine, the outer parts really didn't look very good. So I spent quite a long time to cope with that. What I did, I basically masked the areas here which were not noisy, okay, the good bits, and then with a little pen, in effect, a little paintbrush, I spotted out every star in the whole field. That probably took me a little while. And then you can essentially just reduce the noise level by smoothing everything but the stars in the central part. So it leaves the stars sharp, but gets rid of all the noise. And that was the result that came out. This is, by the way, is the running man. Can you see a man up here? It's a reflection nebulae around those stars. That's the trapezium there, and that's called the fish's head. So that, and you can just see some of the nebulosity around here. So that's quite a tricky thing to do, and I'll come back to that at the very end. Okay, there are 1 or 2 chapters that describe things which would help anything. And to take longer exposures, we tend to do something called auto-guiding. I'm not going to go into any detail, but the idea is very simple. You have a second telescope, this one, with its own camera, and that's linked up to a piece of software in your computer. And that then sends commands to this camera and out of the camera through a cable into the mount. So what the guide camera does, and the guide scope, it sees if the guide star is moving a bit from where it should be, rock solid. and it then sends commands to your main driving mount just to tweak it, to keep it in the right place. Do you get the sort of idea? And that means you can take much longer exposures and possibly sharper images. And this is M13, which is a lovely globular cluster. That's the image that was coming out of the CCD camera that was taking the image. Now that looks terrible, but they stretch it so you can see what you're doing, not overexposed. This is what comes out of the guide's car. Here it's all over the place, but can you see it settle down here? And basically that's plus or minus 1 pixel. So it's moving very, very little on the guide camera, and hence not very much on your main camera system. And that was the result that came out. And the nice thing is that in the heart of the globular cluster, which is here, can you see individual stars? If that wasn't being guided very accurately, that would just blur out. Do you see the point? So it can help you. You don't always need it, but it's there if you do need it. Okay, now I discovered I'd taken that picture of Orion in the winter, the one I showed you. I tried to do it in the summer, or that wasn't quite summer, it was sort of late spring, and the result wasn't at all good. So I thought about it a bit, and the problem is thermal noise. It's called dark current. The amount of noise that the actual sensor generates is a function of temperature, and it varies quite a bit. And the problem is that when you actually have a DSLR camera taking continuous pictures, the sensor temperature goes up perhaps by 12 degrees Celsius, and it gets quite noisy. And if you have a look at this, that is 5 minutes at 20 Celsius, and that's 5 minutes at -5. Can you see it's quite a big difference, isn't there? So I thought, well, how can we cool our camera to keep the sensor a bit colder? And there's one very cheap way of doing it. By the way, this just shows you what happens. Two examples. Starting at 20, it got up to 32. Starting at about 14, I think, or at 12, it got up to here. I can't see it, 24, 23. It's about 12 degrees. So how can you stop that happening? Well, what I did was to take a 1.7 litre food box. There's a type which has a sort of a cover that fits very tightly. Do you know it stops air getting in? Now, I had a hole in it. That's the problem, because the plastic is very brittle, so I had to burn it. A skewer, in the flame of my gas oven, and gradually burnt it around. Otherwise, the first one I made just cracked. So there we go. And all you do, you put some insulation in, and I've actually done it with layers of net, very fine net mesh, and also silver foil. You know these space blankets? Do you ever remember when Heathrow was closed down for at least a day or so because of snow? My wife and I spent our 40th wedding anniversary under one of those blankets on the floor in the Heathrow terminal on our way to Cuba, as it was. Anyway, a layer of those. Now, can you see the thermal space blanket? That's very good at stopping heat transfer by radiation, but that's why they have thermos flasks, same thing. But the little net in between them, can you see it makes lots of little areas, little pockets of air, and that actually acts as quite a good insulator. So that's what's done. And then all I did, I actually cooled the camera in the fridge for a bit. You put it in a plastic bag with some desiccant so it doesn't get stuff condensing on it. Put it into here, and then surround it by some of these somewhat flexible ice packs. Does anyone know about them? Some of the ladies might, perhaps. And that actually has a big effect. It takes the temperature down, and then when you start observing, it goes up again. But you've gone down by quite a number of degrees, by 6, I think. But look, if that wasn't there, this would have gone up by 12. So that's 18 degrees difference. And for every 6 degrees, you get a doubling of the noise. So the noise was reduced by 8 times, and that's the dark current, and the thermal noise there, the noise part, by √8, which is not too bad. So it's a useful thing. Now you can buy, oh, by the way, that's me taking one picture with it. It doesn't look very elegant, does it? But anyway, and there's another one coming up as well. The other way of doing it is to Peltier cool it, and you can actually buy Peltier cooling boxes, about £150. But in fact, what I did was to buy a 15 quid Peltier unit from eBay, and same type of box. You have to slightly alter how it goes. I haven't got the insulation in, but you get the idea. The trouble is, this takes 6 amps at 12 volts. So you need quite a big power supply. But that will then cool things down just as well as the thermal ice packs, but it will do it for longer. And of course, if it's much colder, it will actually get below Celsius. So that's quite a nice thing to do. And that's just showing you what happens. It goes down, and when you start observing, it goes up. So you are a good bit, 14 down to 8, 6 degrees below the ambient, as opposed to being 12 degrees above ambient, 18 degrees in all. So, another problem. I've had a go, using that, imaging what's called M27, which is a lovely planetary nebula, one of the brightest in the sky. I live in Macclesfield, about a mile from the centre, and it is somewhat light polluted. That was a system I was using, a somewhat bigger telescope. This is the guide camera, I was guiding it. Can you see the rather elegant cooling box there? And in fact, I tend to drive things from batteries. The cheapest type of battery to use are the ones they use for golf buggies. You get 22 ampere hours for about 30 quid, which is a lot cheaper than some of the other systems. However, can you see all the light pollution? You can see something here, but this is all red, isn't it? It's not very good. So what can you do about it? Well, you can actually play a trick. And I think I worked this trick out a few years ago. What you do is you make a second copy. I'm just going to show you a second copy. And on the second copy, there's a wonderful filter in Photoshop called Dust and Scratches. It's meant to restore, old pictures. What do you think it thinks stars are? Dust. So it gets rid of them. Now, it can't get rid of the nebula because that's quite big, but you can clone that out, so you've then got a pretty good image of the light pollution. Do you see the point? You've got rid of everything else. So if you then difference that with your original image, you get rid of the light pollution, you can begin to see the nebula, and you can play around a bit, and that's what you get. This is the central star. It's the remnant of the star. It was the nuclear fusion reactor. It's the core. It's probably about the size of the Earth now, still very hot. It's called a white dwarf. I'm told the name is changing to White Dimensionally Challenged Object before long. Okay. Now, there are other things you can do about light pollution. You can buy filters. And much of the light emitted by that nebula, and all these emission nebulas, is in the H alpha. You know the red colour I've mentioned already? But also in O3, which is green. That's the colour of the air glow that I showed you earlier as well. So what you can do is you can get a number of different filters. These two specifically only let the regions around H beta and O3 in the green and H alpha here. This is the best one. I didn't have that one when I took the next pictures, but I had that one. This one here is meant for imaging galaxies and things. It lets a lot more light through, but cuts out this whole region where most of the light pollution is or was. What's going on with all our lights in the roads now? LED. They haven't done my road, but they've done all the next door ones, and they have a much broader spectrum. There's less light pollution, which is good, but it won't be quite so easy to get rid of, I think. Anyway, that's a problem. So I used one of these filters, and this just shows you the effect. I was actually looking up at the clouds, so that's what you got, the same exposure. That's all of the light pollution. The CLS filter works very well, gets rid of nearly all of it. The Barda one, not bad. This one here, even better. And I used this one, because I hadn't got that one at the time, to image the M27. That's just the filter characteristics. Now that's what I had before, without the filter, and that's with. Would you agree that's a lot better? It is, isn't it? So that makes life much easier to get rid of any remaining light pollution. And again, I got rid of the stars, cloned out the nebula, and that's what you get, and that's the result there. Not looking an awful lot different, but in fact you have a chance of seeing more of the fainter parts of the nebula. So that's a way of combating light pollution. Oh, that was the result, which isn't too bad. We don't tend to see colour with our eyes in astronomy at night, but I was at the Isle of Man. They have a wonderful observatory, a 16-inch telescope in a very dark location on the far side of the Isle of Man. And one night, several of us saw the central part of M27, a lovely iridescent green. It was It's one of those things I will never forget. There are some things you've seen that you don't forget. I saw the impacts of Shoemaker-Levy 9 on the surface of Jupiter way back in the 80s. You know, things like that you stick in your mind. Okay, using the same filter, which helps the H-alpha to come through, I took quite a long time exposing the region of sky in Cygnus where there are two rather nice nebulae. This is called the North American Nebula, and up here is the Pelican Nebula. And that's the result I got. So here you've got, this is the Gulf of Mexico, not really of course. I think this is where Trump goes at weekends, somewhere down there. And can you see the pelican up here? There's his eye. This is his rather hook beak down here. So that actually can work very well. So it's a very useful filter to use. Okay, now, planets are a problem because they're quite small. And I imaged Mars, as you will see, a couple of years ago when it was closest. It was only 15 arc seconds across. The trouble is that the atmosphere, the turbulence, typically mucks things up by at least 2 arc seconds. Can you see you've got a problem? Well, what do we do about it? Quite a few years ago now, Philips brought out a very sensitive webcam called the 2UCam Pro 2. And when they discovered that lots of astronomers were buying it, they put the price up by quite a bit. But the idea is this, it's a webcam. You take a whole video stream, all right, of the planet. There's then a wonderful piece of software that looks at all those images. It finds the sharpest, because it can tell which are sharp, because sometimes it's called lucky imaging. The atmosphere is a little bit calmer, you're looking through, you get a better image. So it picks the best ones, it lines them all up, and can give you a much better image than even you could see with your eyes. And that was a picture of Saturn I took many years ago with that 2Cam Pro 2. I'm not saying it's brilliant, but it was one of my first attempts at a planet. Now you can buy specialized webcams. I've got 3 actually, and this is one, it's a color one which I use. Now there's a real problem. Their sensor is tiny. It's just a few millimeters across. You've got to get the planet onto it, haven't you? And that's hard work. So what we do is we use what's called a flip mirror, and basically you have the mirror this way, so can you see you're seeing with your eyepiece? So you can center Jupiter, whatever it is, with that, and if you get it right, that's in focus, the camera will be in focus, parfocal is the word, and you flip the mirror and hopefully it's there. Do you get the point? You have to have a fairly sturdy mount because you don't want Jupiter to drift off the sensor while you're taking perhaps 2,000 frames. And here is an example. I did in fact take 2000 and, can't quite read it, 2003. I was aiming at 2,000 frames. And this is Registax, one version of it. You show it one picture and it analyzes it. This is a Fourier transform. So it knows about Jupiter, right? Then it goes through all of those 2,000 images and aligns them. It gets them all lined up. And it basically puts them in rank order of goodness. So what happens then, it actually does a little bit of adjustment there, and it's showing you a sort of a goodness graph. This actually was pretty good. This is the wiggles here, how much it's had to shift. But that's the graph showing you how bad it was. And then you stack them. Did I go too fast? You can choose how many you want to stack. I've got rid of all the worst ones. Do you see I've got rid of those spikes there? I've only used the ones that haven't had to shift very far from the average. And you stack those and you get a result, which you can see a bit of detail. But Registax has got a wonderful method of sharpening. It's called wavelets, and no one else has done anything better. And that can be used, and you can get a better, sharper image, which you can then export. And that's the image at the top there. Can you see the great red spot? That's getting smaller. This is, in fact, red spot Junior, forgive me. And that's the same picture, but I was just highlighting the various bits to go on the web. Now, that's not brilliant. It's about as good-ish as you can do in the UK, because the atmosphere is never that good. Have anyone heard of Damien Peach? He takes wonderful images of the planets. You don't know how he does it, but he takes a 14-inch telescope to Barbados, where the seeing is near perfect. And the images he produces are fantastic. And this was Mars, day after closest approach. I was using quite a small telescope. That's the 1 arc second resolution. So I've only really got 15 by 15 elements, but in fact, would you agree there's a little bit more detail than even 1 arcsecond? It's done very well. And this is a program called WinDupos. This is what I should have seen roughly, but you agree it fits quite well. Again, Mars is quite hard. It has been very small the last few apparitions, but over the next few, it's going to get bigger and bigger for about the next 8 years, I think, so a bit more chance. Now, I talked about imaging the moon with a DSLR. You can do it with a webcam. And because you get rid of the atmospheric effects to some extent, your images can be sharper. So what you have to do is to take a webcam sequence, a video, and then you need to analyze it. Registax does it, also a program called AutoStackArt2, which the Kogneski, if that's the right word, it isn't, they're actually using now, but I don't get on too well with it. Anyway, I have analysed some lunar things with it, and this is Sinus Iridum, and here is the crater Copernicus. Can you see the tiered walls and the central peaks there? And this is Plato, and this is the Alpine Valley. Now, it's not brilliant, but it's not too bad. And what you then do, you've got these individual segments, we call them panes, and there's a wonderful program which is free called Microsoft ICE, Image Composite Editor. And all you do is you pop your frames in, there were 4 here, and it puts them together perfectly. I get amazed. And that's the image that came out of that, slightly enhanced. And this is another one I've done. These are little individual parts of the segments that went together. There were probably 20 segments to make that image there. And that's, in fact, the whole moon, I think, which I think took me 40 segments. It takes a little while to do this. And the hope is you cover it all. A friend of mine did exactly the same image, I think on the same night, and he missed a bit out. Isn't that frustrating? But luckily, we were able to take my image and pop the bit in he'd missed out, so that was quite good. Now, Jupiter came very close to the moon a couple of years ago, and so I did, I think, 20 panes to do the moon. I then did, with 1 exposure, I then did a different exposure for Jupiter. Can you just see the 4 satellites? Another exposure for satellites and put them all together. Now, that's a slight cheat, because Jupiter really was about here. But if I'd made it that far away, the picture would have been a bit small, so I sort of brought it slightly closer. It could have been like that, wasn't quite. You should. Okay, now, this is interesting. The effects of the atmosphere affect the blue part of the spectrum worse, and as you go towards the red, the effects are least. And they're even less bad, if that's a good word, English, in the infrared. So one thing you can do is to image in the infrared. And I've had a go at that recently. I bought an appropriate filter that lets the near infrared through. And this is one image I did, which is not too bad. And that's another one. Now, you can't really see on this screen, but that resolution is about 1 arcsecond. It's about as best as any one person can do, because I think there were 40 frames, 40 panes in that. And if you try to do the whole moon at twice the resolution, can you see the number of panes goes way up, and you haven't got time. There's a wonderful image which is linked to on my Night Sky website. Just put Night Sky Jodrell into Google. It's called the World Record Lunar Image, and they had 10 people all working simultaneously doing different bits of the moon. It's a fantastic image. Okay, well, we're getting on. Solar observing. You can be very careful, because it's the one thing that can really hurt you. You can lose your eyesight if you don't do it properly. So what we have to do is to have some means of vastly reducing the sun's brightness. And here I've used a filter. It's a Mylar filter, metallized, that cuts out 99.9 something % of the sunlight. And then with the DSLR you can simply take a whole image of the sun, and you can see some sunspots across here. That's when the sun was a little bit more active. It's going down to solar minima now. How long it will remain there, we don't know, but it's a bit quiescent at the moment. And that's, in fact, using a Barlow just to up the image size a bit to see them in a little bit more detail. You can colour them, and that's a typical colour that one might use to make the sun look a bit more like the sun. And again, one lot of this is that lot, made a bit bigger, and that's that lot up there. Now, you can do the same trick. You can use video imaging of small parts, and this is what I've done. These are the 2 regions. This is that one at the bottom. This is the one at the top. and it shows a lot more detail because you've got a chance of mitigating the effects of the atmosphere. Now, there's another way of doing it which actually is better. It's called a Herschel wedge, and in here is a prism that reflects only about 5% of the light this way towards your camera, and the 95% go into a sort of a heat trap down here. But actually this one's got a little image on it, so you can use it as a finder. I've got another solar finder here. That's the sun in the center, so I'm aligned with the sun. That's still too bright, so in here they have some neutral density filters to cut the light down by quite a bit, and also what they call a solar continuum filter, which is a very narrow band in the lime green, and that's the image you get with a camera. Can anybody see a little dark bit down there? Yeah. Well, that was the one little solar sunspot group that was left, and I then did webcam imaging using this setup, and that's the image I got. And you can begin to see the solar granulations, which is nice, and I promise you that's about as good as you can do from the ground. Those Herschel wedges are absolutely fantastic, but they're not exactly cheap. But anyway, that was very pleasing. Now, you can also observe the sun in the light of H-alpha, that lovely deep red colour, and you get to see a lot more detail in the surface. You have to have a special type of camera, solar camera. They use some very clever optics, a thing called an etalon, to basically cut out all the light except from the very narrow band where the H-alpha emission is. And you have to tune them to get them just right. And then you can take pictures showing a lot more detail. These are faculae. That's a prominence. These are obviously sunspot regions. These faculae basically are those things seen against the background, so they look a bit darker. And they're the prominences. They don't tend to be so bright, so you can actually expose for them and add the two together. So that's the sort of thing you can do. That's only obviously part of the sun, so you can use Microsoft Ice and try and put them all together to make a full composite. And this is what I took last May, and it actually shows Mercury. Do you remember there was a transit of Mercury last May? In fact, I was very lucky to get this because I'd been in France doing a photography trip, and I arrived in the morning at Poole, and it was cloudy there, but I was told by my wife it was clear in Macclesfield, so I drove from Poole to Macclesfield fairly quickly, and luckily, by the time I got home, it was still there, and I took that picture. So that's really quite pleasing. And again, you can take nice pictures of really good prominences that happen sometime. There. Okay, well, all of that's been done either with a DSLR or a compact camera, or with those little webcams you can get for a couple of £100 or so. As you advance, maybe you feel it's the time to start using what are called CCD cameras. And the major difference is that they have Peltier cooling attached to the sensor, and that means you can get the sensor down to about -20 to -30. So the noise level, can you see, goes way down, and that makes your camera much more sensitive. There are two types. The first type is called a one-shot colour camera, and it's basically a colour camera. In fact, in this one is the one I happen to have at home. The sensor came out of a Nikon 50D, I think it was. Anyway, you know, a Nikon camera of 2006. So it's just a standard DSLR sensor. But the key thing is that it's cooled, so it works a lot better. And I've used that to image the Andromeda galaxy, which is our nearest giant galaxy, as I'm sure you know. And that was the image I got, having stretched it. Here's Andromeda. This is M110, that's M32. They're two daughter galaxies. Now, you can make that look more impressive. You can make the galaxy look a little bit more dynamic. The trouble is, if you apply the effects to do that to the whole image, all the stars blow out. You know, not good. So using that same dust and scratches filter, you can actually remove the stars. So there's just the nebula, and there are the stars. You can then enhance the nebula. I show you, you know, it's a bit more dynamic, and then you put the stars back. So that's a way of doing that. So that's a one-shot colour camera. You can also buy, at some expense actually, probably big ones starting at about £2,000, monochrome cameras. And the one I have is 8.3 megapixels, and I cool it to about -30. And there's several things you can do. you can do what's called narrowband imaging. You tend to have a filter wheel, because these things are monochrome. And this is my own filter wheel. I've opened the top up. It's got white light imaging. You'll see why it's called luminance. Red, green and blue. Can you see you can make colour pictures with red, green and blue? But also there's a fifth slot, and that's H alpha, which is very useful. So what I did, do you remember in that picture earlier on I mentioned it was slightly reddish around Orion? Well, this is Orion taken with one of my nicer cameras, a full-frame DSLR. Standard picture of Orion. It's got some nice feature. No real red, because this camera isn't modified to look at the H alpha very well. But then I use my CCD camera with an H alpha filter to get the H alpha. Do you see there? This is called Barnard's loop, and this is called the angelfish. Now, can you see the arms of the angelfish? And then you can sort of put them together, which is quite nice. So that's quite a nice thing to do. And that's one, and I've also done the region of Mount Cygnus. Do you remember the North American Nebula? A lot of people call it the North American Nebula, but they don't own it, so it's the North American Nebula. They'd probably like to. And there's the Pelican Nebula, not so good. And this is rather lovely. It's around a star called Sadir, and this is called the Butterfly Nebula here. So you can do some very nice things just combining RGB with H alpha. Now, there are people that, because they're in light polluted locations, use 3 very narrow band filters to do their imaging, because that cuts out all the light pollution. And something that's become very popular and initiated by the Hubble telescope is what is called the Hubble palette. And what they, it's there. I'm seeing 2 pictures here, it confuses me slightly. Okay, now what they do, and I think this is slightly naughty, S2 is the line, is a very, very deep red. They make that red. But H alpha, which is really red, right, I proved that, they make that green. And O3, which is green, they make blue. It does give you some beautiful images. Look at that. Isn't that lovely? But astrophysically, it's not really right. All that green ought to be red. Do you see what I mean? But I have to say they look beautiful. So I haven't really got into that. I have done some narrowband red, H alpha for red, O3 for green, and a narrowband blue filter for blue. And that's actually worked quite well, but I won't show you that. Okay. And then the final thing I'm going to show you is called LRGB imaging, which a lot of people do. L stands for luminance. You tend to take a high resolution image in white light, expose it for quite a long time to get lots of detail. You want a high resolution, high detail image. You then use R, G and B to take individual images through the red, green and blue filters, and you combine those, as I've done here, to make a colour image. The resolution of that doesn't need to be so high, so there are some tricks you can play to make the camera more sensitive. What you then do is to take the luminance image and the colour image, luminance and colour, and combine those together to make an LRGB image. And that's one of the best pictures I've ever taken. I'm not saying I was cheating, but I was remotely using a telescope high in the Spanish mountains, a lovely telescope. And there are a lot of telescopes around there now, around the world now, that amateurs can use. You pay so much, perhaps $50 an hour, to use them. But it means you get some clear skies. We've had hardly any clear skies in Macclesfield the last few months. I don't know what it's been like down here, but it's not been good for us. It's clear, it was clear when I came in, and maybe if I get home and still awake, I'm going to try and do Jupiter, which will be getting around south at about midnight. Okay, so that's basically covering most of the things that I talk about in the book. They have got, very nicely, some books for sale next door. The first book I wrote for CUP was basically an amateur's guide, as you can see, to imaging and observing the heavens. And it was meant to be, and is, it's to fill the gap between the books for beginners and the very detailed books about individual topics. Springer produced a lot of those. But this is to cover that gap. And it's done all right. I'll come back to that. Then, as you know, I was Gresham Professor, and a couple of years ago we produced, less than that probably, we produced basically a book version of my lectures, updated to middle of 2013, I think it was, maybe 14. and they have that as well. And this, of course, is the one that we're here to talk about, The Art of Astrophotography. Now, it hasn't been reviewed yet. I have no idea what people will think about it. I can only really say two things. One is my 3 previous books, there was a textbook as well, they're all 5 stars on Amazon, so there's a bit of a track record. But one thing perhaps more sensible. A colleague of mine, David Tolliday, in my Macclesfield Camera Club, which I've been involved with for a long time, he's a very good nature photography, but he's decided he'd like to do some astrophotography. He's got a very nice lens, 500mm lens. And he asked for my advice, and I told him precisely, and I mean precisely, how to go about imaging and processing the Orion Nebulae. And the one I said was quite tricky. And he did that. He entered it into the Astrophotography award I forget the quite name of the prize. Anyway, it's run by the Royal Greenwich Observatory. And they get thousands of superb images. And with that image, he won the Sir Patrick Moore Newcomer's Best Image Award. So I feel quite pleased about that. So presumably at least some of the information, some of the advice in here can be useful. So if any of you do buy the book, I hope you'll find it so. And the final thing to say is all books get out of date and there are new things that come along. And since Christmas I've set up, it's a blog, but I don't like the word blog, I call it a digest. And I'm adding about 2 essays, 2 pages to it every month. And one of those is an update to the Gresham book. You know, we discovered the binary, the merging of 2 massive black holes. I've talked about that in one of the essays. But there are also essays to update the astronomy books. So that might be worth finding. Notice there's 1 R. That was the original spelling of Morison until some grocers decided to add 2 R's around the late 1800s. But that's found, it's also linked to from my night sky page. Just put night sky Jodrell and that will find it. And I'm hoping there'll be articles there. I've got 3 articles, 3 different months, saying everything I know about refractors, why they work, why they're good and so on, what you might buy. So I hope some of that might be of interest. And over the years, I hope to keep these 3 Cambridge books fully up to date. So anyway, that's it. Thank you very much for listening. Cheers.